Alright, so I think this is recording, or at least I hope it is. We're looking at a second review packet of Skill 4, which was polynomial and rational functions. And here they're asking us to determine the zeros of this function. Zeros are also just another word for x-intercepts. They're also called the roots of the function. And we want to also not only describe where the graph intersects the x-axis, but how does it intersect the x-axis? Does it cross it, or does it just come down and do a touch and turn? Does it just touch it? We can determine that if we rewrite this in factored form, and in factored form we'll be able to identify all of the zeros and identify whether they're multiplicities or even or odd. So let's jump in and do that. If we don't have an X method or any method that I'm aware of that is really going to help us factor this this third degree polynomial, except the rational zero theorem that we learned in this section. So we need to use it. We look at the factors of the constant term, and that's going to be my possible numerator. So the factors of 3, I've got 1 or 3, plus or minus 1 or plus or minus 3. The factors of my leading term are going to be my possible denominators. And so for 4, I've got 1, 2, and 4. So a list, I don't know if this graph is going to intersect the x-axis, but if it does, and if it crosses it at a rational number, it'll be within this list that I'm going to generate right now. So these are my numerators, and I'll use first the denominator of 1, so I just get 1 and 3. Then I'll use a denominator of 2, so I'll have 1 over 2 and 3 over 2. Then I'll use a denominator of 4. Alright, so 1/4 and 3/4. So now I'm going to jump in and do one of two things, or you can do one of two things. Plug the numbers into the function to see because remember, this is the x's, and if you plug it in, the output of the function will be the y values, and if you get a y value that's 0, then you're on the x-axis. You haven't moved up or down. So rather than plugging them in the function, however, I'm just going to go ahead and jump in and do synthetic division. So I'm going to start with 1. I'm going to start with the integers and save the fractions for last if I have to do them. So I'm going to use 1. My polynomial is in standard form, that the exponents are in descending order, 3, 2, 1, and the constant term. I have no missing terms, so I don't have to fill in any zeros. So I can just put 4, 8, negative 1, and 3. Now, and I'm looking at this remainder over here and hoping to find one that has a remainder of 0. Then I would know that the value there is a 0. It is an x-intercept of the function. But here it doesn't look to me like I'm going to get 0. Let's see. If I pull the 4 down and I multiply and I add and I multiply and I add, and here I get 4. That's not 0. So 1 is not a 0 of this function. So let's try negative 1. 4, negative 4, 4, negative 4. No, that's not gonna do it either. I don't get a 0 there. Alright, so let's try 3. Pull the 4 down, multiply, add, multiply, add, multiply. Yeah, 3 is, something less than 150 plus 3. That's not going to be 0, so it's not 3. I'm not even going to bother doing the multiplication there. I can see it's not going to be 0. Let's try negative 3. That might work. 4, negative 12, negative 4, positive. There we go. Positive, and this is 1, and that's a negative 3, and that's a 0. So we found it. Okay. So what does that tell us? Well, it helps us to factor this g of x. And that's the only way we're going to determine the zeros is to solve this equation. We set the output of the function equal to 0, let y equal 0 in order to find the x-intercepts. Well, to solve this equation, I don't have it. I have a quadratic formula. There is, I take this back, there is a formula for solving x cubed, but it's not anything that's easy to memorize, and it's never really talked about, I don't think, in high school mathematics, but there does exist a formula. I just don't know it. I don't think I've ever memorized it. I just know it exists. This is much easier to do it like we're doing it here. So this minus 3 in factored form is x plus 3. And now this guy, well, we can see that that's the constant term, that this is the linear term x, and this is x squared. So what we have, this x to the third factors to x plus 3, and now 4x squared minus 4x plus 1. And you might be able to do your x method, or you might hopefully would be able to see that this guy's a perfect square, that we have 2x minus 1 quantity squared. If 2x times 2x is 4x squared, 2x times negative 1 is negative 2x times another added another negative 2x, negative 4x, and negative 1 times negative 1 is positive 1. So the solutions to this then, let's go ahead and construct our table. And here we're interested in determining whether it crosses or whether it does a touch and turn. So x plus 3 equals 0 gives me x equals negative 3. The multiplicity is 1, which is odd, so I know it's a cross. Over here, 2x minus 1 equals 0, so x is 1/2. Hopefully you can read my writing. I'm not writing very clearly. This tablet's not cooperating. The multiplicity is 2, which is even, so it's doing a touch and turn. That's what it wanted for number 16, so let's move on. Well, let's find the problems. There we go. So let's do this number 17. Same direction, same idea. Now we do want to always, I should have mentioned before that our first step is always to look to see if we have a greatest common factor. So when I set this equal to 0 to solve this, the first thing that I notice is all these numbers are all even numbers. They're all divisible by 2, and all of them have at least an x to the third, so I'm going to factor out a 2x to the third. What I have now in my first term is x to the fourth, because 3 plus 4 is 7, minus, well, 2 times the negative 8 gives me negative 16. 3 plus 2 gives me x to the fifth, and 2 times 16 gives me the 32. So this guy is in quadratic form. Now I can come in and try to, the rational zero theorem would definitely work, but there's a faster way to just recognize that we can factor this to x squared minus 4 times x squared plus 4. X squared times x squared is x to the fourth. X squared times 4 is 4x squared. Oops. That should be negative. I'm glad I was walking through that. I wouldn't have noticed if I hadn't checked. Because negative times negative is positive 16. So x squared times a negative 4 gives me negative 4x squared. And then we have negative 4 times x squared for another negative 4x squared, for a total of negative 8x squareds. So let's continue factoring this. X squared minus 4 factors to x plus 2 times x minus 2. And then I'm going to have another x plus 2 and another x minus 2. So rather than writing them out here and then recognizing, well, hey, I've got 2 of them, I'm just going to go ahead and make the exponent 2 now. I don't think that will cause anybody any problems. So if we make our table, I have my zeros, how does it intercept the x-axis? Is it across or is it a touch and turn? That's what we want to indicate here. So we have if x is 0, then that whole product is 0. And x to the third, the multiplicity is 3, which is an odd number. And when it's an odd number, it intersects the x-axis. It just crosses through it. Now here at x equals -2, since the multiplicity is even, it's doing it. You can call it touch, or I call it touch and turn. Here, x equals +2, 2 minus 2, that's an even multiplicity, so it's another touch and turn. So that's what they wanted there for number 17. So now the directions are changing. We're now, also the function is changing. Before, up at this point, we've been working with polynomial functions, and now we're working with a ratio of polynomial functions. We're working with rational functions. It's asking us to questions about the graph of this function to determine if it has any holes, and if it does have any holes, give the location, give the x and y coordinate for the holes, and if it does have any vertical asymptotes, give the equation for the vertical asymptotes. So the first thing I need to do is factor my numerator and denominator completely and look and determine to see how it reduces, this, if it does reduce. I notice that both of these are divisible by 2. They're both even numbers. And then I have a difference of squares, so I'll be able to continue factoring. Here I have x that appears everywhere, so I can factor that out and get 3x squared minus 10x plus 8. And now in this numerator, I have x plus 2 times x minus 2 gives me x squared minus 4. With 3x squared, I'm going to need a 3x times an x. And here, since this is positive and this is negative, these are both going to be negative. If I have 2 and 4, if I have positive 3 times the negative 2, that's a negative 6. And then negative 6 minus 4 gets me a negative 10. If you can't see that by trial and error, well, you can definitely do the x method like we did before in a previous video, or you can ask me about it and I'll go through it with you, but I need to hurry here, and I know it doesn't seem like I'm hurrying. I wish I could play this speed at like twice the speed back to you because I do talk so slow. I see a common factor, x minus 2 and x minus 2, and those are the only common factors I have. When I have a common factor like that, it creates a hole in the graph. So I know that I'm going to have a hole in the graph, and I need to determine the x and y coordinate. The x coordinate is pretty easy. 2 minus 2 gives me 0, so x equals 2. Now, if I were to plug 2 back into the original expression, I would just get 0 divided by 0, and I don't want that. So I have to plug it back in. To get my y coordinate, I use the reduced expression, this 2 times x plus 2, and this x times 3x minus 4. So if we plug 2 into here, what do we have? Well, we've got this 2. 2 plus 2 is 4. So in the numerator we have an 8. And down here we have a 2. 3 times 2 is 6, and 6 minus 4 is 2. These 2's cancel each other, and 4 divided by 2 is 2. So my hole has coordinates 2, 2, if I haven't made a silly arithmetic error. And now, to determine the equations for the vertical asymptote, I look at the reduced fraction, I look at the denominator, and I can see that there are 2 vertical asymptotes. I need to give equations for vertical asymptotes. Here, 0 is thrown out of the domain, and it will appear in the graph as a vertical asymptote, so I know it's the line x equals 0. I don't care about you writing the word line, but it does have to be an equation. And here, 3x minus 4, we'll add 4 and divide by 3, and it's the vertical asymptote x is equal to 4/3. So we found the location of the hole, and we found the equations for the vertical asymptote for this rational function, a ratio of polynomials. Let's look and see if the next one isn't a similar problem. Yeah. So it's the same idea. So we need to factor both the numerator and denominator. X squared is common to both here. And when I do that, I have x plus 5. And in the denominator here, x squared minus 25 factors to x plus 5 times x minus 5. So I can see that this factor of x plus 5 divides with this factor of x plus 5 to give 1. So this reduces to x squared over x minus 5. So since I have a canceled factor here, I know I'm going to have one hole in the graph. I need to provide the location of that hole, the x-coordinate and the y-coordinate. The x-coordinate is pretty simple. X plus 5 equals 0. Well, hey, x, negative 5 and positive 5 gives you a 0. Now we plug negative 5 into this expression, and in the numerator, negative 5 squared is 25, and in the denominator, negative 5 minus 5 is a negative 10, and both of those are divisible by 5, so I have a negative 5 over 2 as my y-coordinate, because that reduces to negative 5 halves. Now, I have one vertical asymptote. I look to the denominator after I've reduced it, this x minus 5, and I have a vertical asymptote of the line x equals 5, because I set this equal to 0 and solve, and 5 minus 5 equals 0. So there's my answer for 19. Now, for 20, to determine the end behavior of a rational function, I compare the degree of the numerator against the degree of the denominator. And the degree of the numerator is 1. The degree of the denominator is 2. And I just refer to that as being bottom heavy. That's not a technical math term. But whenever it's bottom heavy, the end behavior is a horizontal asymptote. So my horizontal asymptote is the line y equals 0. It's always the x-axis when it's bottom heavy. So what does that mean? That means that when you're very far away from the origin, when you're out here, the graph is getting close to 0, and it's either getting close to 0 from above or below. It's getting close to 0 here from above or below. So as x is approaching negative infinity, the y values are getting closer and closer to 0. That's what it means to be a horizontal asymptote of y equals 0, is that you're getting closer, the y values are getting closer and closer to 0. And for these rational functions, they're doing it on each side. So that's what it wanted, and I think some people were confused. They didn't make the connection that of what a horizontal line is. So we have the same direction. So again, we want to compare the degree of the numerator against the degree of the denominator. So my degree of my numerator is the biggest x. Since this is in standard form, I just look, well, yeah, it's in term by term, which also happens to be standard form, but the biggest exponent on my variable x is 3, so it has degree 3. This also happens to be in standard form. Its degree is 2. It's top heavy, so there is no horizontal asymptote. This is not becoming horizontal as you get away from the origin. It's as you get away from the origin, it's either going to be going up over here or down over here, one of the two. And on the left, as x is going to negative infinity, it's either going to be going up or it's going to be going down, because horizontal would mean that it's getting level as it goes away from the origin, and it's not, because it's top heavy. Alright, so we need to determine as x goes to negative infinity what's happening, and as x goes to positive infinity what's happening. We know it's not going to go towards a number that's going to go towards one of the infinities. And we can use these leading terms. These other guys are not going to come into consideration if we're very far away from the origin. So if I'm evaluate this function g when the x's are extremely negative, when I'm heading towards negative infinity, in the numerator I have a negative number, negative 5, and then I have a negative base raised to an odd power. And the negative base raised to an odd power is going to be negative, but negative times negative is a positive. So I don't know what the number is going to be as x gets very, very negative, but I know it's going to be a positive number in the numerator. In the denominator, I have a positive number times this negative, it's getting extremely negative, but then I'm squaring it. I have a negative base to an even power that's going to be positive, and a positive times a positive is positive. A ratio of positive numbers is positive. So when x is going towards negative infinity, y is actually going up towards positive infinity. Now we need to use that same approach and plug in positive values of x as x is very, very far to the right. Well, the numerator is a negative number times a positive base raised to an odd power, and a negative times a positive is going to be negative. And in the denominator, I have a positive number times a positive number squared. That's going to be positive, but this ratio is negative, so this is negative infinity. Alright, let's look at, what is the next one, 22? Yeah, same direction, same idea. Compare the degree of the numerator against the degree of the denominator. The degree of the numerator here, the biggest exponent on the variable is 2. The degree in the denominator is also 2. When the degrees are equal, we have a horizontal asymptote again. But it's not the line y equals 0 like when it's bottom heavy. We use the leading coefficients. Negative 6 divided by a positive 3 is negative 2. Well, I don't know if you can hear it, but that's loud thunder out there right now. Maybe I will be here for a little while, or unless power goes out. That'll stop the video. Oh gosh, I hope I didn't jinx myself by saying that. Alright, so the end behavior is a horizontal asymptote. It's a line y equals negative 2. So as this graph gets very, very far away from the origin, either to the left or to the right, the output of the function, the y value, is going to get very, very close to negative 2. So as x is going to negative infinity, y is going to negative 2. As x is going to positive infinity, boy, the lights just blinked. Man, I hope... Oh gosh, now I really am getting scared. Not scared of the thunder, but scared that I'm going to have to redo this video. Alright, hey, that's my answer for here, the end behavior. Let's move on to the next one. I think we're getting kind of close to the end. I don't remember how many problems there are. Gosh, there's another. Alright. Describe the end behavior during a thunderstorm. Hopefully the end behavior is not a tornado. I don't think this time of year it would be. Alright. The degree of the numerator is 3. The degree of the denominator, boy, I can hear you. If I can hear it coming down with these headsets on, it's really pouring out there right now. So the degrees are equal. At third degree, the polynomial in the numerator is of third degree, the polynomial in the denominator is third degree. So the end behavior is a horizontal asymptote. It's a line y equals, vertical asymptotes are x equals, man, it is super loud out there right now. So I take a ratio of the leading coefficients, negative 4 divided by negative 1. And negative 4 divided by negative 1 is positive 4. So as x is moving, as you plug in extreme negative values, the y value is getting closer and closer to 4. It'll never, far away from the origin, it'll never equal 4, but it's getting super close. Now I don't know if it's 4.0000001 or 3.999. I don't know if it's approaching 4 from above or below, but they're not asking me for that much detail. And here, again, I don't know if it's approaching from above or below. Alright. So, What do we got? What do we got? All right, vertical. They're asking about horizontal, about asymptotes. So for the um, for the vertical asymptote, I have to factor this and write it in reduced. Write this fraction in reduced form. So if I look at the numerator, I see an x is common everywhere, and I have 2x squared minus 5x minus 12. And in the denominator, I have an x that's common everywhere, and then I have 2x squared plus 11x plus 12. Alright, so I can probably factor this further. Let's look and see. The 2x times x will give me 2x squared. Now, negative 12 has several different possibilities, and the middle term is also negative. So I could have negative 12 and positive 1. I could have negative 6 and positive 2, or negative 4 and positive 3. So which do we want? Is it easy to see? I need that middle term. What if I tried negative 4 here, which give me negative 8, and a positive 3 here, and negative 8 plus 3 is negative 5. Boom, there it is. If you can't do that by just looking at it and trial and error in your head, do your X method. And if you need help with the X method, why, talk to me. Here again, I'll try to see if I can factor this. If we can't, it's possible this could never equal 0, but I doubt if it's that we gave you one like that. Let's look. 2x times x gives me 2x squared. This time, since this is positive, the middle term is positive, both of my factors here are going to be positive. So 1 and 12, 6 and 2, or 3 and 4. Let's try 3 and 4. Let's see if 2x plus 3. Yeah, 2 times 4 is 8, and 8 plus 3 is 11. So there it is. So this guy has 2 holes in it. Now it's not asking me for holes, but I don't want to call a hole a vertical asymptote. This and this cancel. This factor and this factor cancel. But it's not asking me about holes. It's asking me about vertical asymptotes. And I have my reduced fraction x minus 4, x plus 4. And of course that only reduces if x is not 0 and x is not negative 3 halves. But here I look in the denominator, x plus 4, and my vertical asymptote comes from that denominator, and it's the line x equals negative 4. Don't forget to write it as an equation. Now, for the horizontal asymptote, we compare the degree of the numerator against the degree of the denominator. So I'm going to erase all this. I don't need to see that in factored form to compare to determine the degrees. The degree of the numerator is 3. The degree of the denominator is also 3. So there is a horizontal asymptote. It's the line y equals. When it's bottom heavy, it's y equals 0. When the degrees are equal, we just divide the leading coefficients. 2 divided by 2 is 1. So there we have it. We have one vertical asymptote and one horizontal asymptote, and there's the equations. Now the next one is probably a similar. Nope, it's asking us for even more. Alright, so we can do that. And it's not as loud up there. It must be calming down a little bit. But I still want to hurry. So for the x-intercepts, I let y equals 0. So I need to factor this. So let's... Boy, that numerator, I'm going to have to think about that and maybe use my rational zero theorem. The denominator. So here, let's write this out and come back to it in just a second. Let's look at this guy. 18, well, x plus 6 times x plus 3. Now, I don't know, it's possible in trying to hurry and create this review for you. Did I make a typo? Was this supposed to be x squared? Or let's assume now that it's not, that it is x cubed, because I don't remember what the answer is going to be. If I'm trying to factor this, I'm going to rewrite it as x cubed plus 0x squared minus 13x minus 12. And I'm going to look at factors of 12 for my possible numerator. So I've got 1, 2, 3, 4, 6, and 12. Now fortunately I'm pretty lucky that my leading coefficient, my possible denominator, is just positive or negative 1. So my list of possible rational zeros, rational solutions to this equation might be in this list. So I'm going to do synthetic division and look and see if we can find it. So see, the list looks a little bit long. That I just modified our old test to be a quick review of this. So I never intended, and I'll proofread the actual retake better, I never intended for you to have to go through this many possible zeros in the list, because I could spend time right now to go through all this and have none of them be 0, and maybe I had a typo. But let's continue, because for practice purposes it can be illustrative. Alright, so the 1 comes down. Negative 12, well, that's not 0, so boy, the lights are starting to blink again. Alright. Oh, and I heard the thunder. I wonder if you heard it. Yeah, that was a good one. Oops, that's not. Pay less attention to the thunder and more to what I'm doing. Negative 1 times positive 1. Then I get, hey, I get a negative 12. And I get a positive 12, so I do get a 0. So now I'm beginning to wonder, hey, maybe that was good. Maybe we actually intended that for that to be like that, because now, and it didn't take us that long to find it now. So negative 1 worked. So in factored form, that's x plus 1. So this x cubed minus 13 minus 12x, let's erase this, and we know what it factors to now, or at least the partial factor. The x minus 1 in factored form is x plus 1. And this is x squared, 1x squared, minus 1x, minus 12. So I'm going to erase all of this, because I don't need my rational zero theorem now to try to factor a quadratic. So this guy factors to x plus 1. This factors to x minus 4 and x plus 3. And this guy is x plus 6 and x plus 3. So, yeah, this was good. This was not a typo. The x plus 3 and x plus 3 is creating a hole in the graph. So I know that the coordinates of my hole, or at least the x coordinate, is a negative 3. I know that x equals negative 3 is not going to be a vertical asymptote. This over here, this x plus 6, x equals negative 6, is the equation of a vertical asymptote. Now, if I'm finding an x-intercept, then I want to set the output of this function equal to 0. We've already canceled those. There's no other common factors. If this fraction reduces to 0, it's because of the numerator. The denominator can never be 0. So, see, I needed to make sure that you don't call a hole an x-intercept. So I have two x-intercepts. I have an x-intercept. This graph crosses the x-axis at x equals negative 1, and it crosses it at x equals 4. Now, while I have this reduced, let's go ahead and get our y-coordinate here. Let's plug in a negative 3 plus 1, a negative 3 minus 4, and a negative 3 plus 6. Because if I would have taken that negative 3 and plugged it into the original, I would have gotten 0 divided by 0, which is undefined. So, and remember, I'm not trying to find a point that's on the graph of f. I'm trying to find a point that I guarantee is not on the graph of f. It's a hole in the graph. Alright, so negative 3 plus 1 is a negative 2. And here I have a negative 7. Well, that's going to be positive 14. And here, 6 minus 3 is 3. So I'm getting this crazy integer 14 divided by 3. Alright, so now for the y-intercept, we plug in 0 into the function. So I don't need this factored form anymore, so I'm going to go ahead and erase it. You have it in case in case we do need it. So for the y-intercept, we input 0. And in the numerator, that's 0, that's a negative 12. And in the denominator, that's 0, that's a positive 18. Both of these are divisible by 6. So I'm getting a y-intercept of negative 2/3. Now, to determine this end behavior, we compare the degree of the numerator against the degree of the denominator. The degree of the numerator is 3. The degree of the denominator is 2. So there is no horizontal asymptote. So these y values have to be either positive infinity or negative infinity because there's no horizontal asymptote. So let's plug in we've got it over here. Let's plug in a negative value into our function. Now, when we're very far away from the origin, x cubed dominates over this x and this 12. They really do not affect that number at all why did I put negative 1 there when I just wanted the idea of a negative value? I guess the thunder is bothering me again. So in the numerator, and down here in the denominator, when you're far away from the origin, 9x and 18 are not going to affect this value x squared. X squared dominates. This exponent makes that value much larger in a negative or positive sense. It's squared in a positive sense than the others. So if we plug in a negative value into this function, my numerator has a negative base raised to an odd power. My denominator is a negative base raised to an even power. That numerator is negative. This denominator is positive, negative times, so that ratio is negative. So when x is becoming, as you move to the left, very far to the left, then these y values, it's going down towards negative infinity. Now, what about when we plug in positive values? When you move very far away from the origin to the right, what's going on? Well, in the numerator, you've got a positive base raised to an odd power, a positive base raised to an even power. That's a positive divided by a positive, which is positive. So this is going to positive infinity. All right. Last one, and it's very similar to the last one. So we have this rational function, a ratio of polynomial functions. And we want to factor the numerator and the denominator. X is common to both, so I have x times x plus 3. And here we could either use the x method, or since this is a prime number, we can probably figure it out. We've got two numbers that multiply together to give us a negative 21, and they add together to give a negative, so the larger in magnitude is going to be negative. So let's try negative 7 and positive 3. Negative 7, positive 3, 2 times 3 is 6, and negative 7 plus 6 is a negative 1, so boom, we found it. Alright, so this x plus 3 and this x plus 3 cancel each other out, creating a hole in the graph. A hole in the graph, we want to provide the x and the y. So the x is very easy, it's negative 3. If we want to provide the y, we just plug in negative 3 into this reduced negative 3 in the numerator. 2 times negative 3 is negative 6. Negative 6 minus 7 is a negative 13. The negatives cancel, and I have 3 over 13 for my whole. What didn't cancel in the denominator is 2x minus 7. So that's going to create a vertical asymptote. If you set that equal to 0, you'd have to add 7 and divide by 2 to solve it. So you have the line 7/2. Now, to determine the x-intercepts, we don't want to call this x equals negative 3 an x-intercept because it's not part of the graph. There's a hole there. So we want to look at this fraction in reduced form. So we set the output of the function to find an x-intercept equal to 0, and we use the reduced fraction Now, if a fraction reduces to 0, I guarantee it's because of the numerator. So I know that this graph is has an x-intercept of 0, so it's passing through the origin. So I know over here this y is better be 0 as well. But let's double check that. If we input 0 into the function, that'll give us the y-intercept. So in the numerator, we have 0 squared plus 3 times 0. And in the denominator, those are 0. And 0 divided by negative 21 is 0. So it's exactly what we expected, that since x was 0, that it was going through the origin. So y is 0 at the origin. The degree of the numerator is equal to the degree of the denominator. The degrees here are both 2. So it has a horizontal asymptote. And the horizontal asymptote, if it were bottom heavy, would be y equals 0. But since the degrees are equal, it's a ratio, it's 1/2. So when you get far away from the origin to the left or to the right on this rational function, these y values are getting closer and closer to 1/2. If you need to convince yourself of that, go to that Desmos graphing calculator and graph that and zoom out and see what's happening on the graph if you look far to the left and far to the right away from the origin. So hey, I hope this helps, and I'll talk to you later.